Hi, let's talk a little bit about gravity. We're going to keep this short and sweet, but try to give you some of the crucial basics about Newton's universal law of gravity. So before we get into super technical stuff, we should talk about this minor thing. So there are some words that in normal speech are like, just seem like normal words, and weight is one of them. But that once you are in a context like physics or astronomy, the word weight actually has a really specific meaning that's not exactly the same as the meaning we use in normal speech. In this equation right here, this is for calculating weight. This is weight, weight, which is measured in a unit called newtons, has a very special meaning, and the weight is the amount of force that gravity exerts on an object. So, key idea, weight is a force. Um, this thing over here is mass. And mass is not the same thing as force. In fact, mass is like almost the opposite of force. Like force is a thing that pushes and makes things move, or more specifically, makes them change their state of motion. Mass is the thing that resists that change. So the difference between you give a bowling ball a shove and you give a beach ball a shove, well, that feels pretty different because when you shove the bowling ball, it has a lot of mass. It resists that shove in a way that the beach ball doesn't. And by resist, I don't mean the force of that mass, I mean the inertia. It's not easily taking off. So mass, think of it as resistance to change. This is the mass, and mass is measured in kilograms. And then this thing here, we'll put a little that little g there, that is the acceleration of gravity. People often look at this and they're like, oh, it's the strength of gravity, it's the force of gravity. And it's not really either of those things. It's the rate at which gravity accelerates objects wherever it is that you're doing this problem. So g is the acceleration of gravity. And that thing, g, if you are at or near the surface of the planet Earth, that has a value of about 9.8. Sometimes it's convenient just to say 10 because it's so close to 9.8. But the actual number is 9.8. So near the surface, g is equal to 9.8. So what that tells us is we can compute the force of gravity if you're near the surface of the Earth by taking the mass of a thing and multiplying by 9.8. So let's do a very simple calculation that we'll revisit in a bit. So let's say here's the surface of the Earth, person, and let's say that this is a 70 kilogram person. How much weight does that person have? It's not the 70 kilograms. I know, like if you go somewhere and you buy, a kilogram of something, they're talking about the kilogram weight. This is not a weight. This is a mass. We want to know the weight in newtons, right? We're going to say the weight is equal to mass times gravity. Mass is 70. Gravity, and I'm going to call it 10 just because I don't have a calculator handy. I'm going to say gravity is 10. And so the weight is going to be equal to 700 newtons. So the force on this person that gravity exerts is around 700 newtons. Pretty simple. The catch is we're often not at the surface of the Earth. So we need something more general form. We need something more general purpose. And that more general purpose thing is this. And this is really the most crucial thing to know about gravity. This is called you know, I'm not 100% sure whether it's Newton's universal law of gravitation or Newton's law of universal gravitation. Not sure. So I'm going to identify the things that are in this equation, and then we'll talk a little bit about what the equation means, and we'll come back and apply the equation. So this equation tells us how much force gravity exerts on an object. Now, here's something that's really important to know about gravity. We think of gravity as like, oh, the gravity of the Earth, but in fact, gravity is a force of interaction. It's a pulling force. Gravity can't push, unlike lots of other forces, which can either push or pull. Gravity can only pull, and it's a force that exists between any two masses at all. They don't have to be planets, they don't have to be stars, they could be tiny. You could have two eggs next to each other. There's going to be a gravitational force between them. Gravitational force of attraction between two eggs is so small as to be almost not measurable. It actually is measurable. It's very hard to measure. You measure it using something called the Cavendish balance. We're not doing that. So this law is supposed to tell us about the force of attraction between any two masses. And I'm going to just actually leave it like this and just point out that the force of attraction between any two masses is this number G times M1, which is one mass, M2 is another mass, over R squared. And let's talk about what all of that stuff means. So first, let's talk about this. So get a planet. It's near a star. And the star pulls on the planet. And it pulls on it with some force of gravity. Now, this shouldn't surprise you at all. If this star were to suddenly grow, or we replaced it with a bigger star, right? The bigger star, well, we're going to get more force. So, you're near a big star, big force of gravity. Small star, small force of gravity. Likewise, if the planet grows, the planet gets bigger, that also makes this force bigger. The force of gravity between any two things depends on the masses of those things. And that's what we see right here. This right here, that's the mass of whatever your first thing is. And this right here is the mass of whatever your second thing is. I wrote those like capital and lowercase. They don't have to be. I actually, when I'm in a rush and I don't want to have little subscript 1, subscript 2, I'll write this as G, big M, little m over R squared. Not because one mass is big and one mass is small, although in this drawing it does look that way. I write it just so that you get two different masses with different symbols. Right? Lowercase. You actually draw them so that they have symbols. So the force depends on those two masses. Make one of them bigger, you make the top of the fraction bigger, you make the whole thing bigger. So that's the first thing. Depends on the mass. What else? I have another one of these pictures here somewhere. No. All right, I'm going to work right here. Here's another thing that's really important, is that if our star is here and our planet is here, and we got some force of attraction between the two of them, if we take the planet we take the planet, wow, not paying attention. If we take the, there we go. We take the planet and we move it farther away, the force gets bigger. This is not working. We take the planet and we move it away, the force gets smaller. If the planet's farther away, less force. If we move the planet closer, we get more force. So closer, stronger, farther, weaker. What's this R? Oops, that's that R right there. So the R is in the denominator. What it means is, like, if that number R is big, the force is weak. Farther away, weaker force. Closer, stronger force. And notice that notice that this R has a little 2, it's a squared. This is sometimes called an inverse square law. And it turns out in physics there are lots, or in all kinds of science, there's a lot of inverse square laws for interesting reasons that we're not going to talk about right now. But this is an inverse square law, meaning when that R value, which is, did I fail to mention that R is the distance between the two things? And maybe I did. That R, that's supposed to be the distance between the two things. Maybe I need to re-record this. Anyway, so this is an inverse square law. It's not just that, if you double the distance between the two things, right, then the 2 in the bottom, this gets bigger, force is going to get smaller, the force will be cut in half. It's that it's affected by the square of the distance. So if you double the radius, then the distance squared becomes 4 times as big, and the force gets a quarter the size. What we see is the following, is that if we have something and we're like, okay, my object is some particular distance away, and we have some particular force, that if we get closer, that this is going to go way, way up. And if we get farther, this is going to go way, way down. And we end up with a curve that looks like this on our graph, where if you're close in, big force, far out, small force. Inverse square law. But what about the G? What's this thing here? That, it turns out, has nothing to do with the system. It's not like we go and we measure G. G turns out is just, it's a number that makes the units come out right? That essentially what we're saying is this force gets bigger if one of the mass gets bigger, it gets bigger if the other mass gets bigger, and gets smaller if the distance between the two gets bigger. But when we actually multiply and divide all these things out, we want to end up with a force in newtons, and we need to just pick the right proportionality constant if that turns out to be a really small number. This is the universal gravitation constant. Remember, little g, that's the acceleration of gravity near the surface. This g is something you would use for any gravity calculation. And it's a very small number, as I mentioned. It is, if I can do this right, 1, 2, 3, 4, 5, 6, 7, 8, 10. It's that. It's very small. That's so small and so inconvenient to write that we never, ever write it out that way, which is why I had a hard time remembering how to do it. We usually write this in scientific notation. We say that G is equal to 6.67 times 10 to the minus 11th, and then this has some crazy units just to make the units come out right. Newton meter squared per kilogram. 6.67 times 10 to the minus 11th. By the way, if you're not used to taking a number like that and sticking it into a calculator, the way you're going to put it into a calculator is you're going to write 6.67, and then you hit that exponent button that has the 2 capital E's, and what you get is this, and you go E negative 11, but you don't push the minus sign. You hit the like change sign with little parentheses. So it's E to the negative, where E stands for exponent. So that's how calculators like to see scientific notation. That's how we write this very tiny number. So we're going to use this to redo. We just did, let's see, how do I point on like that? There on the screen, we figured out the weight of a person using a nice simple method. Let's figure out the weight of the same person using a less convenient method, using Newton's universal law of gravitation. Okay? Not that important in astronomy to figure out the weight of a person, but it's a good exercise for other things. So let's do this. So weight equals the force of gravity. And so the force of gravity is going to equal to big G, big M, little m, r squared. Okay. We've already said what G is. G is going to be 6.67 times 10 to the minus 11. This right here is going to be the mass of one of our objects. What are things they're attracting? Well, the person is being attracted by the planet. So what's the mass of the planet? Now we have to find the mass of the Earth. I don't know. Hey Siri, what's the mass of the Earth in kilograms? Here's what I found. 5.9 times 10 to the 24th. Mass of the Earth. And then what's the mass of the person? Well, we already said that the mass of the person was 70 kilograms. And then R is how far is the person from the Earth? Now this is important because if you're standing on the Earth, what's the distance between you and the Earth? It's 0. You don't want to put a 0 in there, right? It makes math very angry. So it turns out that that distance between two things is actually the distance from the center of one thing to the center of the other for reasons I'll mention in a moment. So this is, right, if here's our planet and here's our person, right? The distance from the center of the person to the center of the planet is basically the radius of the planet. So what we want here is the radius of the planet. Hey Siri, what's the radius of Earth in meters? Meters, not in kilometers. if you ask for kilometers or you look something up in kilometers, you need to change it to meters. This does not work if you put in kilometers. 6.37 times 10 to the 6th. That's about what I remember. 6.37 times 10 to the 6th meters. Okay, so calculator. Calculator. (6.67 E11 sine 5.97 E24 times 7 times 0.37 E6 squared divided by. Oops. 686, 687, which is, where's my pointer thing gone? I'm supposed to put it down looking for the, what did we say last time? We said it was 700, and if instead of using 10, we'd actually use 9.8, we get basically this. So this is an example of using Newton's universal law of gravitation, or law of universal gravitation, and finding out some force value. One other thing that I need to mention before we go on is the following. So gravity is like, here's a thing, here's a thing. Gravity pulls the two things together. But like, what if we have a big thing? Right? What if we have a big thing? Well, the thing has parts, right? Like I could cut this up and cut this up. Like, do the parts of the thing attract each other? Or like, what if we took this planet and we sliced it up into lots of little chunks, right? And now we put our person on here, and we're like, oh, what's your weight now? Is it the same as it was before? Well, it seems like it would be really weird if the force of the planet changed just because we had cut it. If there was the same amount of stuff there, and in fact, if we go like, oh gosh, now we have to say like, how much gravity pulls on our person? How much is our person pulled toward this chunk, and how much is our person pulled toward this chunk, and how much toward that chunk, and how much toward this chunk, right? So we could do that problem. It's a really hard problem to do. Here is something really beautiful. Not going to try to prove it to you. Got to take it on faith. It turns out that this, you get exactly, if this is a sphere, if this is a sphere, then this is the same as if all of the mass of the planet were all packed dead center. So, this whole planet has some mass, big M planet, and now we're going to say, oh, we're going to crush it all down into this one little dot. And it turns out the math works out exactly the same. That if we say, oh, instead of figuring out the attraction of this person to all the little parts of the planet, we let's pretend all the planet's in the middle, that the person is some distance away, r, that's the radius of the planet. We get exactly the same thing. And this is a good thing, my friends, because what that means is that anytime we want to calculate gravity between two things, we just measure from the middle of one thing to the middle of another thing. It's also important to remember that gravity is acting in terms of distance at the middle. Is that, suppose obviously it's silly that the size of this person compared to this planet is kind of like Little Prince-ish. But, if we had a little satellite flying around here, right, and it's zooming around this planet, and we wanted to know what's the force on that satellite, well, here's what we're not going to do. We're going to go, all right, what's the force? The force is GMM over R squared. What's R? R is the distance between the two things. We're not going to do this. We're not going to be like, oh, there is the distance between the planet and the satellite. No. That's the distance between the satellite and this little chunk of planet. But if we want to know the distance between the satellite and the planet as a whole, we're going to find out this distance, right? How far is the satellite from the middle of the planet? So that's like the height of the satellite above the surface of the Earth plus the radius of the Earth. Okay, so that's Newton's universal law of gravitation, right? Newton's universal law of gravitation, the force of gravity is equal to G, the gravitational constant, an extremely small number, 6.67 times 10 to the minus 11th, times the mass of one object times the mass of the other object, divided by the square of the distance between the two objects, where if they are big objects, we measure from the center of one object to the center of the other. Gravity. Go forth.